Well, students, in the last class, we have studied significant digits and we have understood what is meant by loss of significance. And also, we have now seen the danger of losing significant digits in our computation. In this lecture, we will study propagation of relative errors. What is meant by propagation of error? Well, from one step of your computation to the next step, when you perform the calculation to reach that next step, you would have seen in the last class through examples that your error may get amplified or increased, mainly due to loss of significant digits. And further, in the later steps, as you go on increasing your calculations, your error also gets amplified, and this process is what we call as propagation of error. It is important to understand what are all the arithmetic operations and other operations like square root and so on can amplify the error, and what are all the operations that rapidly amplifies and what are the operations that doesn't amplify the errors that rapidly. These kind of ideas are very important when we are doing scientific computing, especially when you are dealing with a large scale scientific computing. This knowledge is very, very important because you may be working with a method which is mathematically very accurate. You might have done a sophisticated analysis and seen that your method mathematically is very good and accurate. But if you have a bad handling of these arithmetic errors, then you may finally land up in a numerical solution which is still bad, although your method is good. Therefore, one has to understand how these relative errors propagate in our calculation. It is better to do a basic mathematical analysis on certain operations, especially the basic 4 arithmetic operations, and have a good idea about in what all the situations that we encounter loss of significance that can significantly amplify the error. So today we will try to set up a base to analyze the propagation of relative errors in our computation. Let us start with the propagation error in addition and subtraction. Let us denote the true value that we would like to consider as xt, and its approximate value is denoted by xa, and let xt equal to xa plus epsilon, where epsilon is a small number. This means epsilon can be written as xt minus xa, which is nothing but the error in xa when compared to xt. Similarly, we'll take another value yt, which is the true value that we would like to use in our computation. But instead of this, our computer is taking a approximate value. Let us denote it by ya, and the difference between them, that is the error, is denoted by eta. For definiteness, let us assume that both xt and yt and also xa and ya are positive real numbers. Now we would like to evaluate the sum of the two numbers xt and yt. As we have taken, our computer is going to consider the approximate values xa and ya instead of xt and yt, and thereby our computer will be giving this value instead of this value. Now the question is, what is the relative error in xa plus ya when compared to xt plus yt? Well, by definition, we can see that this is nothing but the true value, that is xt plus yt, minus the approximate value, that is xa plus ya, divided by the true value, that is xt plus yt, right? Now let us eliminate xa and ya using these two expressions, and that gives us xt plus yt minus, instead of xa, we will put xt minus epsilon, plus instead of ya, we put yt minus eta divided by xt plus yt. We can cancel xt with this, xt and yt with this yt, and therefore we get epsilon plus eta divided by xt plus yt. Now the same idea can be followed to obtain the relative error in xa minus ya when compared to xt minus yt. So let me combine both together and give you the calculation. We want relative error in xa either plus or minus ya when compared to the corresponding arithmetic operation between the two true values, that is given by xt plus or minus yt minus xa plus or minus ya divided by xt plus or minus yt. Plus or minus, it depends on whether we are taking plus or minus. In this, as I told, we will eliminate xa and ya, and thereby we have this, and that can be simplified to this. Now you see, for addition, we have epsilon plus eta divided by xt plus yt, that is your relative error. Whereas for subtraction, we have epsilon minus eta divided by xt minus yt. Since we have taken both xt and yt to be real numbers, we can see that xt plus yt is non-zero, and generally, assuming that this epsilon and eta are very small, we can see that this is a very small number. So it means the relative error involved in xa plus ya when compared to xt plus yt is in general very small, provided the error that we committed in the initial values, that is the value that the computational device takes instead of what we want. If the error is very small, then after the addition, the relative error in the sum when compared to the sum using true value will also be very small. That is what this calculation shows. Therefore, doing an addition on a computer is in general a safe operation. Now come to the relative error in the subtraction of two numbers. Again, we may be taking xa very close to xt, and therefore epsilon may be very small, and similarly eta also is very small, and that makes this number to be small. But you look at this, if xt and yt are very close to each other, the true values are very close to each other, then you can see that this is a very small number. If that number is much smaller than this, you see there is a danger that this can be very large, right? So you see that subtraction gives us a possibility that your relative error may become very large even though your initial error epsilon and eta are very small. Therefore, the conclusion is the above calculation shows that the relative error propagates slowly with addition. I hope you understood now what it means. Whereas the relative error may be amplified drastically with subtraction, especially when the true values xt and yt are very close to each other. Therefore, whenever you are subtracting two numbers, you have to be very careful. If the values of these two numbers are very close to each other, there is a danger that the relative error may be amplified drastically. You can see that if you have two numbers xt and yt which are very close to each other, it means what? The first few digits in the mantissa are same. This can be otherwise told that there is a large number of significant digits in xt when compared to yt, or yt when compared to xt. And when you go to subtract them, we tend to lose those significant digits, which results in the loss of significance. And that is increasing the relative error in the subtraction drastically. And that may lead to the amplification of the relative error drastically. Next, let us study the propagation of relative error in multiplication. The relative error in xa into ya when compared to xt into yt is by definition given like this. And remember, we have taken xt is equal to xa plus epsilon and yt is equal to ya plus some eta, where epsilon and eta are very small numbers. When you substitute xa equal to xt minus epsilon and ya equal to yt minus eta, we get this expression. And from here, you can simplify this expression to get this. Now you see, this can be written as epsilon by xt plus eta by yt minus epsilon by xt into eta by yt, right? And remember, epsilon is equal to xt minus xa. Therefore, epsilon divided by xt is nothing but xt minus xa divided by xt. That is, by definition, er of xa. Right? Similarly, eta by yt is er of ya. Therefore, this expression can be written as er of xa plus er of ya minus er of xa into er of ya. So you can see that the relative error in xa into ya, that is the product of the two numbers, when compared to the product of the true values, is going to be given like this. So if you have small relative error in x variable and a small relative error in y variable, then the multiplication is going to amplify your error rather in the way that it is sum of the relative errors, right? That is, this one is going to be less than or equal to the sum of the relative errors in their input values, provided the relative error in x and the relative error in y are of same sign. This shows that the multiplication will going to amplify the error because it is going to have the sum of the two errors. However, it is not going to amplify it drastically like it may happen in the case of subtraction. Now let us take the division of two numbers. The relative error in xa divided by ya when compared to xt by yt is given by this expression by definition, and that when you eliminate xa and ya, we get this expression. Now you see, you can simplify this expression to get this form, and that further can be written like this. So this can be written as yt divided by yt minus eta into epsilon by xt, which is nothing but the relative error in xa. And for the second term, we will multiply and divide by yt. Xt is getting cancelled here, and yt minus eta you keep as it is, and can write eta divided by, already I multiplied by 1 yt, therefore I will divide by yt. This is nothing but the relative error in ya when compared to yt. This is the relative error in xa when compared to xt. Therefore, we can write this expression as yt divided by yt minus eta, which we can take common, and what remains is the relative error in xa when compared to xt and the relative error in ya when compared to yt. And further, this can be written as 1 by 1 minus er into this. Why? Because you just take yt outside from here and cancel with yt, then you have 1 minus eta by yt, that is nothing but relative error in ya, into this as it. You can see that in division, the relative error is product of this into this term, which is the difference between the relative error in XA and relative error in YA. So this is not going to be a problem. This is going to be just, it's a kind of amplification, but not a drastic amplification. Whereas here, if you see, if this number is almost equal to 0, it means what? Your relative error in YA, if that is going to be almost equal to 1, it means that if you make 100% error in your initial data for Y, then your relative error is going to be very large for division. There is no surprise in this. If you take very bad data, then your result should be bad, right? So as long as you are not making a big error in your initial data, your division is not going to amplify the relative error drastically. Okay, so that seems to be a fair condition. Whereas if you recall in subtraction, even if you make small error in your initial data, the subtraction may amplify the relative error in certain situations, especially when X and Y are very close to each other in their values, right? Such danger is not there in division. So as a conclusion, what we see is plus, multiplication and division are safe to perform on a computer, whereas subtraction may lead to disaster in terms of amplifying the relative error, especially when there is a loss of significance. From the examination point of view, if I ask you to find the propagation of the relative error in an expression, say x plus y into z, say, then what you have to do is take the true value of x as xt and write it as xa plus some epsilon, and similarly yt you take as ya plus some eta, and zt as za plus some nu. Then you evaluate E of XA plus YA into ZA, that is ER of relative error of this. You put the definition of it just like this, and you simplify it into an expression where you only have relative error in X, relative error in Y, and relative error in Z, something like this, and that will be the final expression that is needed. Next is the total error. Here I would like to caution you that there are two ways that we will be defining total error in our course. One I have already mentioned in the first session of this chapter. If you recall, we have two levels of errors. One is coming from the mathematical approximation, which we call as mathematical error. Another one is what we are now seeing called the arithmetic error. The sum of these two is what we will call as the total error. But the total error that I am going to talk now is different from what we will be defining it more precisely later when we are doing different methods. Let us see what is the total error that we are going to see now. Let's recall in the last class, we have seen how a computer does arithmetic operations with n-digit rounding or chopping. You give two numbers, x and y, and you want to do any operation with x and y. What the computer does is first it takes the approximation of x, which we call as floating point approximation, and it takes the approximation of y, that is the floating point approximation. It may be rounding or chopping or whatever. Then it does the required operation and takes this answer, and finally does the floating point approximation of that answer. Okay. So, and that is what it gives us as an answer finally. So this we have explained in the last class in full details. The computed value is therefore this, and what we wanted to compute is actually this, right? And therefore, this computed value involves an error which includes the floating point approximation of your original variables, x and y, due to the n-digit rounding or chopping. And the next level of approximation is once you compute this value, then you do one more rounding or chopping of the final answer. So you have two levels of approximation that happened in this arithmetic operation, right? Now, the total error that we would like to define here is the sum of the errors in these two levels. More precisely, look at this. Here, we want to get this value, but our computer gave us this value. What is the error between these two values? Well, mathematically, what you do is you add and subtract this intermediate step, okay? Therefore, the value that you want minus the computer did it at the first step, this one, and then the answer from the first step minus the further approximation of the answer. So if you add these two, that is going to be your total error. Mathematically, it is just elementary to see it. In this, the first error is called the propagated error because this error happened in our first step and that is sitting in your final answer anyway, right? Therefore, we call it as propagated error, and the second term is called the floating point error. That is, this one is called the floating point error. The sum of the propagated error and the floating point error is what is called the total error. Therefore, in this chapter, if I ask you to calculate total error, you have to find this. In particular, if I ask you to find the propagated error and the floating point error, then you have to use this formula and this formula. Let us take an example where we will try to evaluate the integral in, which is given by integral 0 to 1 x to the power of n divided by x plus 5 into dx, where n is taken to be 0, 1, 2, and so on. There are two ways that we can write this integral. One is in is equal to 1 by n minus 5 into I n minus 1. Note that I naught is equal to log 6 by 5. And now once you have I naught, then for n is equal to 1, you can write I1 as 1 minus 5 into I naught. Now, I naught you can plug in here and get the value of I1. Once you have I1, you can go to find I2, which is given by 1 by 2 minus 5 I1. I'm just putting n equal to 2 here. And again, this value can be plugged in here to get I2, and I3 can be similarly written as take n equal to 3 in this formula. 1 by 3 minus 5 I2. Again, you plug in this value here and to get I3. And like that, you can go on till I20. Remember, when you are finding I20, you would have already found I19. And then I20 is given by 1 by 20 minus 5 I90, right? So this is how you will iteratively find I20. This is what we meant by saying iteratively we are finding. That is, you initially find some value, plug in that and get the next step, plug in that to get the next step of value. Like that, you keep on going. Well, how to see that? It's not very difficult. You can see integral 0 to 1 x to the power of n divided by x plus 5 dx can be written as integral 0 to 1 x to the power of n minus 1 minus 5 x n minus 1 divided by x plus 5, right, dx. So that will give you, if you take this, so it will be x to the power of n plus 5 x to the power of n minus 1, that get cancelled with this, and you will get x to the power of n here. And now you integrate this, you will get x to the power of n by n evaluated 0 and 1 minus 5 times n minus 1 and that is precisely what we have written as our iterative formula. I can also write the same formula, that is this one, in this form. Now you see, you give me any value somehow, don't ask me how we get this value. Somehow, suppose you got this value, then you can go backward. I30 is given to me. Okay, maybe I am interested in finding I30 here. I30 is somehow given to me. Then I29 I can find by putting n equal to 30 here. That is 1 by 5 into 30, 150 minus 1 by 5 into I30. So somehow we got I30 the value. So therefore we can plug it here and just find the value of I29 by evaluating this simple expression. Like that we can go on till you get I naught, which we know of course is log 6 by 5. Okay. Just for the understanding, let us do the calculation of In for n is equal to 30 using forward iteration. And then we also start with the known value of I30 somehow. This is almost exactly equal. It may not be exact, but approximately it's a very good approximation of this. Then we will go back and see whether we are hitting this number correctly. This is just to check the calculations. We are cross-checking how well our computer can work. Okay, we are not trying to establish any method for finding the integral of this, but rather we are just using it to see how well our computer can work for us. So for forward iteration, n is equal to 1. The value using this formula, that is forward iteration formula, is given like this. And what I did, I started with I30, then I computed I29, 28, like that. I kept on going backwards and reached I1, and that gave me this value using backward iteration. Remember, I did many calculations to reach I1 because I started with I30 and then went backward many iterations and reached this value and got this. What is the exact value? Exact value is this. You can just evaluate this and get this value. Now n is equal to 2 gave similarly some other value, but not to make you bored, I just jumped 5 here. Okay, otherwise I could have shown 1 by 1, but I just jumped to 5. Forward for iteration formula gave this. Backward iteration formula started from I30, came backward up to I5 and got this value, and the exact value is this. Till now your computer is working well, both with forward iteration starting from n equal to 0 and reached n equal to 5 using this formula, and starting from 30 and reached 5 backward and using this formula. Both worked well. Now go to 10. You can see again both forward and backward worked very well. Next we do 11, 12, 13, 14, and when we reached 15, we got the value of the integral x to the power of 15 divided by x plus 5 dx, and using forward iteration we got this value. Using backward iteration we got this value, and exact value is this. You can see that there is a slight error popping up in the forward iteration formula, whereas backward iteration was working well when compared to this exact value. Now let us go to I20. At I20 you can see the exact value is 0.007998, right? Your backward iteration gave you good approximation. In fact, it's up to whatever digit shown, it's exactly coinciding with the exact value. But you see, there is a drastic difference between the exact value and the forward iteration. Means something is going wrong with the forward iteration. When it reached 15 itself, it started little bit giving error, and that quickly amplified, and you see that there is a drastic error in this when compared to this value. Let me go further and find I25. The forward iteration value is something 11.74, whereas the exact value is something close to 10 to the power of minus 2, very small number, whereas the forward iteration gave a very big number. Now let me go to 30. You can see that the forward iteration gave you something which is nowhere near to the exact value. Okay, here I have not computed because somebody gave me the exact value of I30 to me. With that, I started my backward iteration and went backward using this formula. In fact, till I reached I0, I was more or less I1, up to I1, I got a very good result. Okay, so it means 30. 30, 29, 28, like that. I'm going again 30 steps backward. I got very good result. Whereas I started with I0 and came 30 steps forward, the same number of steps. Here also I did 30 steps. Here also I did around 30 steps, maybe 29. But forward iteration amplified my error drastically when compared to the exact value, whereas backward iteration did not magnify much. Why it is so? We can see that in the forward iteration, you took the value I0, okay? On the computer, it may be something approximately equal, right? Equal to some value. Therefore, let's call this as I0 tilde. Okay, that's an approximate value to I0. We know that when you go to compute anything on a computer, the computer is not going to evaluate exactly, because the values that it uses may have some rounding errors, right? Because of that, what answer you get may be not exactly what you want, but it may be only the approximate value. So you had some error in this. And that, when you go to find I1, you can see that it was 1 minus 5. I0 I am supposed to find, but my computer plugged in not I0, but I0 tilde. Okay. So whatever error which it had when compared to I0, it was multiplied 5 times when you get I1, which on a computer, again, it's not I1, but it was some approximate value of I1. Let me denote it by I1 tilde. So I want I1, but my computer gave I1 tilde, which is an approximate value of I1. Why that approximation came? Because it calculated log 6 by 5, only approximate value, not exact value. Thereby it had some error. That error is magnified 5 times, and that is sitting inside this. Again, when I go to find I2, I will have 1 by 2 minus 5 times I1 I am supposed to put, but my computer doesn't know what is I1. It only knows I1 tilde, which is the approximate value. So that it plugs in here. Okay. Again, the error which is there in I1, remember, the error was already multiplied 5 times when it went from 0 to 1. Now 1 to 2, again one more 5 times. So the initial error in I0 is now amplified 5 into 5 times, plus the error whatever is committed here, that is the floating point error. Now you see there are two levels of error involved in this. One is the error coming from I0. If you recall from our previous discussion, that is the propagated error. That is the error which is coming from I0. It first came to I1. From I1 it is carried over into the calculation of I2, right? So that error was initially multiplied by 5, and now in this step it is again multiplied one more 5, right? So therefore the propagated error at the second level is actually multiplied 5 square times, whereas the floating point error, which is the error committed at this level, while it was computing I1, it made some error newly in that step, that is multiplied by 5 times. So the total error, therefore, is going to sit here, and that will come into I2, and then I2 will further be approximated, right? It's FL of whatever you compute, right? So that I2 is going to be used in I3, 1 by 2 minus, again you are amplifying 5 times, I2 tilde you will be putting. So that is going to be used in computing I3, and therefore you have 5 times whatever error you committed after computing I2 was amplified by 5 times, and then the propagated error now has 2 steps. 5 square times it is multiplied with the error committed at the I1 tilde calculation, and 5 cube times at I0 tilde calculation. So it is carried over like this, and then you made a new approximation, floating point approximation to the value that you computed here, and that is going to be taken as I3, and it goes on like this. So every step you are amplifying your total error by 5 times. The total error contains your floating point error, which is 5 times, and propagated error is much more than 5 times, right? So that is how your total error is getting propagated from one step to the other step. The total error from one iteration is multiplied by 5 times to when it goes to the next iteration. Now coming to the backward iteration, what is happening? The idea is more or less the same. Your n minus 1 is computed with the help of 1 by 5 n. Well, there may be a floating point approximation here also, but let us just take only this into consideration and see how it goes. 1 by 5 times in you are supposed to put, but your computer must be putting in tilde. So whatever error you carried over from the previous step, okay, 1/5 of that error only is getting included into the calculation of in minus 1. So you are propagating, but every time you are carrying over 1/5 of the previous error. And then you make a new error here by putting a floating point approximation, which we are denoting by I tilde. Now, in minus 2 to calculate, you have 1 by 5n. There will be some approximation here also. Minus 1 minus 1 by 5 into in minus 1 tilde. So whatever error you have committed here, 1/5 of that only you are going to contribute in this calculation, and then this, and whatever you finally find as a difference of these two, you will take a floating point approximation of that, and that is going to be your computed value at n minus second in iteration. So in this way, well, the error is propagating, but at every iteration, the error that you are carrying over is 1/5 of the previous iteration. So you are adding 1/5 of the previous iteration, whereas in the forward iteration, you are adding 5 times. You are amplifying very rapidly, whereas here you are amplifying it very slowly. That is why you see that backward iteration is still very good up to 30. Maybe you go 300 or so. See, we have gone only up to 30 here, but if you go say 300, 400, maybe then when you reach the first step or whatever it is, it may be a big error, but up to 30, you see that it's very good. But up to 30, the forward itself was abnormally bad. So the error that is propagating is in your computation, make your final answer no way near to what you want. Okay, so you have to be very careful in handling computers. Computers are very powerful tools, but they are very, very dangerous. You may be mathematically accurate in your formula. See here, your formula is accurate. There is absolutely no approximation involved in this formula. You start with this and compute this iteratively like a human being computes. You don't have any approximation, but you look at the computer's output. I'm just doing it in a 64-bit powerful computer. In 30th iteration itself, things have gone abnormally bad. Okay. So therefore, you have to be aware of this rounding error, which we call as arithmetic error. So arithmetic errors propagates quite dangerously if we use formulas which are very sensitive to these errors, like the one which you used here, the forward iteration. Mathematically, forward iteration formula and backward iteration formula, they both are equivalent. They both are exact formulas for finding this iteration for any given n, but computationally they make a lot of difference. So in the backward iteration, the total error from one iteration is divided by 5 at the next iteration. So they both are exact formulas. Mathematically, they both are equivalent, but for a computer, one is very, very bad, other is good. So the conclusion is, in this example, as we increase the n, the total error tends to increase drastically in the forward iteration, whereas the total error tends to increase very slowly. It increases, but 1/5 of the previous error only it increases in the backward. So that's the final conclusion of this example. It also tells us that we have to be careful in handling computers while we do scientific computing.